Vector projection. I know, it sounds a little intimidating, right? Like something straight out of a dense textbook. But what if I told you it's actually something you see literally every single day? Today, we are going to completely demystify this idea by talking about a simple shadow. Yep, that's the secret. So let's get into it.
So here's our game plan. We're going to start with shadows, then meet our building blocks, vectors. After that, we'll actually visualize casting a vector shadow, peek at the math behind it all, and then, the best part, see where this stuff is hiding out in the real world. Simple as that?
All right, part one. We're not kicking this off with complicated equations or anything like that. Nope. We're going to start with something we all know, something super familiar, a shadow.
I mean, seriously, think about it for a second. You walk outside, the sun's out, and boom, there's your shadow on the ground. It's kind of like a flattened out version of you, right? It's got a certain length, and it's pointing in a specific direction. That everyday idea, well, that's the key to everything.
And there it is. That's the big secret. The fancy technical term projection is just a mathematician's way of talking about a shadow. Once that clicks, honestly, the rest of this is going to be a breeze.
So to tell this story about shadows, we need let's call them our actors. And in the world of math, these actors are called vectors.
All a vector is, when you boil it down, is something with two pieces of information. How long is it? That's what we call magnitude. And which way is it pointing? That's its direction. How far and which way? That's all you need to remember.
You know, the absolute easiest way to think about a vector? Just picture an arrow. The length of that arrow is its size, its magnitude, and whichever way the pointy end is aimed, that's its direction. Simple, right? It's a really powerful way to visualize this. Okay, time for the main event. Let's get our actors, our vectors, on stage, switch on the spotlight, and actually watch this shadow pop into existence. So here they are. We've got vector A. You can think of that as our object. It's the thing that's going to cast the shadow. And we've got vector B, which is going to act like the ground or the surface the shadow lands on. Okay, now use your imagination. Picture a super bright light source, maybe like the sun at high noon, shining straight down at a right angle, perpendicularly to our ground vector B. Having that light shine straight down is a really important part of this. And there it is. See that? With the light shining down, our object, vector A, blocks the light and throws a shadow. And look where it lands, perfectly flat, lying right along the same line as vector B. And that right there, that visual, that is the entire concept. That shadow that just appeared isn't just like a projection, it is the projection of vector A onto vector B. It's the real geometric meaning of the whole thing. So we've got the picture in our heads. Now let's see how we describe that picture using the language of math. And hey, don't worry about the formulas. They're just a way to write down the cool thing we just saw. Okay, first, let's clear something up that trips a lot of people up. We can ask two different questions about this shadow. If we ask, hey, how long is the shadow? We're talking about a scalar projection. It's just a number, a length. But if we ask, what is the shadow? We want the whole thing, the arrow itself, with its length and direction. That's the vector projection. So finding just the length, the scalar projection, is actually just some basic trick. If you know the length of vector A, that's what those bars around the A mean, and you know the angle between the two vectors, which we call theta, well, the shadow's length is just the length of A times the cosine of that angle. Cosine is basically the perfect tool for finding the length of a shadow. And now for the whole shebang, the vector projection itself. It's kind of like a three-step recipe. Step 1, we do something called the dot product. It sounds fancy, but it just multiplies the two vectors to give us a single number that tells us how much they're aligned. Step 2, we have to scale that number. We divide by the length of vector b squared to make sure our shadow is the right size for the surface it's on. And finally, step 3, we put it all together.
We take that number we just calculated and we use it to give our shadow the perfect length in the direction of vector B. And that's it. That's our shadow vector. Okay, so this is all pretty cool to look at. But what's the point? Why does any of this actually matter? Well, it turns out these vector shadows are hiding everywhere.
Seriously, this idea is fundamental. In physics, if you're pushing a lawnmower, projection calculates how much of your push is actually making it go forward versus just pushing it into the ground. In every single video game or animated movie you've ever seen, the computer is running projection calculations nonstop to create realistic light and shadows. And in data science, it's used to help find the most important information in huge, complicated sets of data. It's a total workhorse.
So look, if you walk away remembering just one thing, let it be this. Don't get bogged down by the formulas or the jargon. At its very heart, a vector projection is just a shadow, a simple idea that's incredibly powerful. So there you have it. The next time you see your own shadow trailing behind you, maybe you'll think about the vectors at play. Now that you have this idea, this mental model, where else can you spot a projection hiding out in your world? Thanks so much for joining me.